Page 17 of complex numbers and polynomials. Number 5, 1 0 of this polynomial here is purely imaginary. Find a and hence factorize p of z into a product of linear factors. Okay, if one of these zeros, and notice that all these coefficients, including a, are real. So if it has a zero which is purely imaginary, then it must also have the conjugate of that imaginary number. Okay, so if I was going to break p of z up into factors, I would say that one of the factors is, and the third factor has to be real, right? Because if you have an odd number of zeros, then one of the zeros must be real. So I have one real factor, one purely imaginary factor, and then the other one would be the complex conjugate of that. So let's say that one of the factors is real, and we'll call that factor r. And then we'll say that there's an imaginary factor, and we'll call that factor I keep saying factor, I mean zero. There's another zero which is complex. We'll call that zero c. Okay, and there is and let's define this as the real c is real, but the factor is c, or not the zero is ci, and then there's a third factor which would be negative ci. Okay, or opposite of ci. So we have one real zero. We had one purely imaginary zero, ci, and we have its conjugate, negative ci. So we can build this polynomial by multiplying together three factors. It would be z minus r, z plus ci, and z minus ci. So we have z minus r, z plus ci, z minus ci. So if we multiply these two together, we get z squared, and we have the inside and the outside terms cancel each other out, and then we have minus c squared times negative 1, so it would be plus c squared, and then we have z minus r here. And then if we expand this, we'll have z cubed plus c squared z minus rz squared minus rc squared. And so I'm going to move these two in the opposite order so that it'll be in the order that we're used to seeing. Okay, so now we compare what we set up here with this. Okay, so basically we got a is equal to negative r. We have 3 is equal to c squared, and we have 9 is equal to negative rc squared. So let's see. Looks like here we can see that c squared equals 3. That leads to c equals square root of 3, right? And if we know that c is equal to square root of 3, then c squared is equal to 3. So we know that 9 is equal to negative rc squared. So negative r is equal to 3. R is equal to negative 3. And if r is equal to negative 3, then a is equal to negative 3, which is positive 3. So a is equal to 3. So one of the things we're looking for is a, and the other thing is we want to make p of z into a product of linear factors. So r is negative 3, so that means the linear factor for r is going to be z plus 3, and then z plus ci, z minus ci is going to be z plus square root of 3i and z minus square root of 3i. So that's it, okay? Okay, so now we're looking at the page 199 reading. The sum and product of roots theorem is very similar to what we already saw for the chapter 1 quadratic roots theorem, sum and products roots theorem. So like if we have a polynomial, and this polynomial is huge, it's the nth root, the nth degree, and it's got a coefficient a subscript n in front of the x squared, x to the n, and then it has coefficients that are numbered by subscript all the way down to a subscript 0, which is the constant term with no x multiplied times it, and then all the others are multiplied times some degree of x. Okay. The sum of the roots of a polynomial is negative a subscript n minus 1 divided by a subscript n. The product of the roots of a polynomial is negative 1 to the nth times a subscript 0 divided by a subscript n. Demonstration. So if you write this polynomial in a different form, which is you're going to have a coefficient which is the same as that coefficient, and then every other constant here is going to be actually a 0 or a root of the polynomial. If you multiplied all these next to all these numbers, x and alphas, with each other and do like a massive FOIL, you would get an expression that kind of looks like that, except it would have alphas in it instead of a's, right? What exactly would that look like? Just to see what that would look like, let's take, it's obvious like the first term would just be all the x's multiplied times each other. So that would just be x to the nth, right? There's x to the nth, okay? Now the next thing you're going to multiply together is you're going to multiply, imagine you're doing like FOIL, okay? So you're going to multiply this times all the x's here, right? Because the way you do FOIL in this case is you pick one of the two terms in each of the linear factors and you multiply them times each other. So imagine that you pick the constant term here. That means that you're going to multiply that one times all the red x's that follow. So what would be the degree of that term? It would be x to the n minus 1 instead of x to the n, right? And it would be multiplied times minus alpha 1. Well, imagine if you did that with every single one of these alphas. Every time you multiply an alpha times a bunch of x's, you're just going to get 1 alpha times x to the n minus 1, right? And when you add all those up together, you're going to end up with this monster here. All the alphas added together times x to the n minus 1. So it's kind of cool how that works out. The reason why this is here is because the coefficient at the beginning, right? So that's kind of cool. All the factors added together are going to be related to the second coefficient of the polynomial, okay? And then of course, if you choose, let me erase all this again. If you choose to multiply together all of the last terms, all of the constant terms, you're going to get this term, which is all the roots multiplied together. And sometimes it's going to be negative and sometimes it's going to be positive. If you have an odd number of roots, it's going to be negative. And if you have an even number of roots, it's going to be positive, right? So that's how you can use the expanded form of the polynomial to figure out what some of the roots are, okay? So let's look at number 1, and maybe it's easier to understand. So first we have a quadratic, which is kind of similar to problems we've done before, 2x squared minus 3x plus 4. So if we use these rules here, we know that if we take negative a subscript n minus 1 divided by a subscript n, that is equal to the sum of the roots. So the roots for this, let's say, are going to be alpha plus beta. So the sum of roots are equal to the second coefficient, which is negative 3, negative of the second coefficient, negative 3, divided by the first coefficient, which is 2. So actually that's equal to negative 3, which is 3 halves. Okay, let's look now at the product of the roots. So alpha times beta is going to be equal to this. So negative 1 squared, which is 1, and a subscript 0 would be 4, and divided by a subscript n, which would be 2, so it's equal to 2. Okay, so the sum of the roots is 3/2, and the product of the roots is 2. Let's do C. So for C, the sum of the roots, which would be alpha plus beta plus gamma plus delta, would be equal to negative, right? Negative, and then a subscript n minus 1, which is negative 1, divided by a subscript n, which is 1. So that would be 1. And then if I multiply all these roots together, then I'm going to get negative 1 to the nth, which is negative 1 to the 4th, which is positive 1, times a subscript 0, which is negative 4, divided by a subscript n, which is 1. So it's negative 4. Okay, let's do E. So x to the 7th, so it's n equals 7 now. And so I'm going to multiply all the roots together. Let's say alpha 1, alpha 2, blah, 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 all the way to alpha 7 multiplied together. That is going to be equal to, or I'm sorry, I'm going to add them all together because I'm going to do the sum of the roots first. So alpha 1 plus alpha 2 plus dot, 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 alpha 7. And that is equal to it's this one, which is going to be negative the second coefficient, which is negative 1. I'm sorry, yeah, the second coefficient, which is negative 1. Oh, and the negative of that, so negative of negative 1 divided by the first coefficient, which is 1. That's also equal to 1. And then if I multiply all the roots together, I get this formula, which is negative 1 to the 7th times a subscript 0, which is negative 9, divided by a subscript n, which is 1. So I end up with negative 1 times negative 9 divided by 1, which would be 9.